Welcome back to our case study on Lake Michigan, page 3. And we're now considering what if phosphorus is not causing this algal bloom. And the reason why we start on this note is because on the previous page, Matt and Flora, in their conversation to Aunt Janet, talk about some laws that were put into place in the 70s. As soon as those laws came in, the phosphorus decreased, and it says nothing about the laws being rescinded or if anything has changed legally on this. So at this point, we're not thinking that maybe it is phosphorus. We're just thinking at one point, many years ago, it was, and we still have those breaks on the system. So legally, nobody can dump more phosphorus in here. So we're starting on the idea of what if it's not phosphorus? If it isn't phosphorus because of these laws, then what is the next thing to think about? So we know that algal growth is limited by light. That's what our sentence says. So maybe something is going on there. Let's look into this and see what we find. So Flora finds out that the Great Lakes also have phytoplankton. So let's take a look at phytoplankton. Phytoplankton are actually rather interesting in my book. When you Google search phytoplankton, so many different images come up. It's just amazing the different types of phytoplankton that we have. And let's zoom in on one of these here. So I'm going to zoom in on this guy right here. And look at that. We have one that is definitely a kind of a tennis ball looking one in the center. We've got long straight rods. We've got curved, how would you describe this? More of an ellipse type of shape. So they come in many different forms, and it looks like they have some chlorophyll in them. They're definitely getting some light energy going on in many of these cases. All right, so phytoplankton, very tiny, and they're getting blamed for water clarity issues. Water clarity issues, when we're talking about that, I like to think of it as either cloudy or clear. So, cloudy or clear. Let's take a look at our figure on the right-hand side now. We're seeing a graph that has years on the x-axis. So there's our x, those are independent. And our y, which is our dependent. So y, and I don't think I have enough space to write in there. And again, years is going to be independent, and that's pretty straightforward. So 83 to 87, we're taking a chunk of time here. Then we have 95 to 98, a second chunk, and then a third, 2007, 2008. What I really would like you to take a look at is this y-axis label right here. Okay, so milligrams of carbon, and if you look here below the figure when they start saying in words what each one of these things is trying to represent. So milligrams, so if you weigh out something in grams, we're going tinier than that. We're going to a milli. And a milli is 1/1000th of a gram. So a milligram is 1/1000th of a gram, otherwise known as 10 to the negative 3 grams. And that's how we're measuring our carbon. And the reason why we're doing this is because phytoplankton, remember, they all look weird, all different shapes, and they're super, super tiny. You would need a microscope to see these. And the only way we can really count them reliably is instead just analyze how much carbon is in a specimen of water. And what is a specimen? It is 1 meter squared. So imagine a meter here, so 3 feet just about, and make a big square. One side is 1 meter, the second is a 1 meter. So a big square box, and that's what they do is they collect a square meter of water, and they consider that per day. So that's kind of a rate thing. And in 83 to 87, we had a high amount of carbon per meter. So if you look at the top of that bar graph here, it's going to come in, maybe at 1,000 milligram carbon per meter squared per day. So this is a lot of organism, many organisms. By 2007, though, it will only get, let's see here, it goes 400, so we're probably 200 right here, milligrams carbon per meter squared per day. So all of a sudden, we don't have that many organisms. Right here, few organisms. All right, so keep that in mind as we go forward on this. Many and few. Visually, what do you see in the water? Well, many organisms are going to make it more cloudy. Few organisms is more clear. So that's the effect. These organisms are so tiny, but they still will, they'll kind of make your water look junky. So they're not completely getting dissolved looking. So you're going to increase the turbidity. That's another way to talk about this. And again, it's all relative, cloudy, clear compared to each other. So let's go back to the question that we've been asked. Describe in words what has happened to phytoplankton in Lake Michigan. I would say that between 1983 and 2008, they have decreased. So from 3 to 2000. So again, you have to give a time frame. Things are relative. Let's go to the bottom of the page now. Matt found a report describing 20 years of data on the water clarity of the lake. How do we measure clarity? Well, we have this thing called a Secchi disk, and it was basically taking readings from a school ship program, and they describe it as a disk. It's a circle divided into alternating black and white quarters. So let's take a look at how this is used. If you just Google search images on Secchi disks, you'll see the actual disk. So there's our alternating black and white right here. And then you'll see its uses. So down here in the bottom, so right under this little area right here, we see that there's a person in a boat lowering the Secchi disk down. And as it goes down in the water, it may remain very clear. So this top image right here is showing, I don't even know if that's in the water quite yet. But as soon as it starts going down into the water, you may not be able to delineate those real crisp black and white lines. And if it goes further down, so in the right side, this picture here showing just kind of what looks like almost a white ball on the string, that's what you'll see as the turbidity interferes or impedes your visual on the Secchi disk. So we have a lot of Secchi disk data, and we're going to move forward on page 4 with this information. But do note that, let's see, in the first years of the school ship program, so last sentence right here, the Secchi disk could be lowered down 6 to 8 meters, and then they would not be able to see the real crisp black and white lines. So let's move on to page 4.